Okay. Hi, people online. Hi, people not online. Um, Thanks for coming to this talk today. I am a pretty informal person, so feel free to just like shoot questions if you don't understand anything or if you want clarification on anything midway through. Um, but yeah, today I'm going to talk about some of my interdisciplinary work on energy transitions in the US, kind of go through a bit of like what I'm doing, kind of how it's being translated into some like data visualization work, some of the research efforts that go behind it. Come in. And talk about some future directions for research too. Um, so yeah, we'll get started. Um, there's a truism among energy historians, and it's that there's no such thing as an energy transition. There's only energy additions. Um, if I were a different brand of energy historian, I would probably be arguing this point quite strenuously. Instead, I tend to argue the opposite for reasons I'll get into. But if you look at something like the overall energy use of the US throughout history, you can kind of see what they're getting at, right? So, like, over time, the US never really took away any form of energy. It only added new ones. All right. So if you look at this, there are no like subtractions of energy. Like when we add a new one, we don't take an old one away. Like energy is never getting displaced. So like the classic examples here are when you look at the use of firewood for American energy history, it has this early peak around the 1880s, 1890s. And it sort of declines a little, but in fact, we're using exactly as much firewood in the 2020s in the US as we did in the 1880s. Similarly, the peak amount of coal ever used in the United States was in the year 2005. The peak amount of oil was in 1973. The peak of natural gas is this last year. So generally, substances are only ever getting. And this is true also if you look at it on a per capita basis, although the story is a little bit different. Like you can kind of see that on a per person basis, there's a lot less use of firewood here labeled as biomass. But generally, you still get the same pattern of like new fuel, great expansion, just kind of stays there over time. And all of this data is from this new project of ours, which is cataloging overall American energy use across time. A lot of this data had been cataloged before, so particularly this side of things, the supply side of things, the amount of fuel that we've used over time has been heavily detailed. But what we were really trying to do was figure out like where the fuels were getting used, what different fuels were getting burned for. This kind of became a collaborative project between me. I'm a historian. And then I'm working with a climate scientist and then a data visualization person and then a team of other people, mostly kind of like undergraduate and graduate students floating around in various interdisciplinary spaces. And the overall kind of like impetus for this project and for this line of thought is what historical lessons we could derive about energy transitions. So like, does history have anything to say about what drives energy transitions, what hinders them? So we built a comprehensive database of energy production and energy consumption, and turned it into a number of visualizations, the kind of like big one being this animated Sankey diagram. So depending on your background, you might be extremely familiar with a Sankey. Since I work in historical spaces, almost no one is, so I'll just do my usual spiel. Basically, on the left side of the diagram, you have kind of origins of energy, so primary energy sources, the various kinds of fuel we're using. And then on the right-hand side of the diagram, you have the various kinds of uses that the energy is getting put towards. And each of the lines between them is scaled according to the flow of that particular primary energy source to a given use. So, you'll see things like the amount of petroleum that we're putting towards transportation, the amount of natural gas that we're putting towards electricity, residential, commercial, industrial. And each frame of this diagram, as the animation proceeds, is a single year, like a picture of the entire American energy economy for a single year. So kind of frozen in time. There's an interactive one that I would love to go to, but as indicated by the AV person stopping by earlier, I have a series of black screens here. So all I'll do is restart the animation so that I can talk about it while it goes to. And each of these lines is kind of a research project unto itself. So like the amount of energy being used in the agricultural sector early on is a question of like, how many horses are there in US society, and how do you compare like a horse to a steam engine? Like you can do it thermodynamically, but in order to do that, you kind of need to know how much is the horse eating, how much of that food is being directed towards its actual work output on the farm. So each of them becomes like a really idiosyncratic research project as well. Incidentally, if you want to go see the interactive version whenever, I would recommend doing it on a desktop rather than the phone that the QR code lets you go to. But it is a really fun tool to just kind of play around with, because you can go to various points in US history and just kind of see different energy transitions happening in real time. But I'd like to get really specific with a single transition, which kind of leads me to the kind of like main points that I kind of want to make today about the differences between energy additions and energy transitions, and this term that I'm playing around with of zombie energy, of like energy that somehow kind of like refuses to go away despite it being abandoned in a large chunk of society. And that specific single transition is the one away from coal energy in the US in the mid 20th century. This diagram shows energy consumption in the residential and commercial sectors. They're grouped together because they're grouped together in the historical documents that we have, because coal companies are kind of tracking whether they deliver to factories or to just retail deliveries to random places on the street, and they don't really make any differentiation between them. We have some attempt to differentiate them in kind of like the depths of our work, but for the main diagram, we kind of left them together. But as you can see, coal kind of replaces biomass, this is firewood, over the course of the 19th century and the early 20th century. This is itself a complicated and actually kind of difficult transition. But I want to focus on what happens after that, which is this precipitous decline around the late 1940s, early 1950s, as people move away from coal stoves and start switching to things like oil burning furnaces, natural gas burning furnaces, and then electricity. And most of this, even towards the end of the 20th century, by far the biggest part of residential and commercial energy use is going towards space heating. That's just a lot more energy inefficient than, or not energy inefficient, but a lot more energy intensive than any other household use. Air conditioning averaged across the whole US uses something like 25% that of space heating. Heating water is like another like 25%-ish. And then electronic appliances are maybe like a third of the overall electricity flow. So coal goes away, and this is a story that's true across several sectors. If I showed you the chart of transportation energy use, you'd see it around the same time. It's getting replaced in locomotives by fuel oil and by diesel as trains start to dieselize. And also, of course, the energy economy more generally is shifting away from railroads and towards automobiles and trucking. It starts to go away also in the industrial sector, as well as steel, is kind of eclipsed by other forms of energy, and especially as steel manufacturing moves abroad in the kind of deindustrialization period of the late 20th century. And this leads coal barons to panic. You see it all over the place in all of their corporate documents. They are genuinely concerned that no one will burn coal ever again. And, fairly so. Coal is an extremely dirty fuel. It's kind of inconvenient to handle. If you have anything that's liquid or gas, then it'll kind of flow through pipes neatly without any kind of labor, whereas coal, unless you have a really large scale operation, someone has to physically like shovel it from place to place. So like if you look at like late 19th century, early 20th century documents, there will be like household manuals about how to handle coal, and like there will be people writing in their diaries about how they discover like Carboniferous era fern fossils in their household coal. So like it's a very different kind of experience of energy than we have. But the upshot of it is that coal is vastly going away, and it's total five-alarm fire in the coal industry documents. But their mines still exist, and all of the infrastructure to move coal from mines to various distribution sites still exists as well. And kind of as you would expect in a situation where demand is dropping precipitously and supply is pretty much the same, that means that the fuel gets a lot cheaper. Yeah, absolutely. Hmm. Great question. So I don't know how the AV would work in this room. So just for the benefit of the online people, I'll just repeat the question. The question is, are the coal companies kind of just coal companies, or are they kind of larger energy conglomerates? Which I'm assuming the like underlying question here is like, would they have a strong incentive to stay with coal? It really depends. Towards the end of the 20th century, a lot of energy is getting conglomeratized, I guess, under larger umbrellas, and you start to get a lot more mergers of coal and oil and gas companies. And of course, the same energy companies now are investing heavily into renewables to kind of like hedge their portfolios. Um, that said, the question is, or the problem is still kind of there, even if they are kind of a multi-energy or multi-fuel company, because otherwise you just have a huge amount of stranded assets. Like the stuff that you use to mine coal, quite aside from just the land, but like the actual physical infrastructure to do it, can't be easily repurposed for anything else. And so the capital assets of the coal companies, I think, uh, I would honestly probably just go and look at our own estimates from the project I'm going to talk about after this, but I think it's something like a few $100 billion today of like stranded assets in coal. Yeah, I think. Um, so it's definitely not something they want to give up. Uh, which leads me to the savior of the coal industry, which is electricity. This is a graph of electricity coming to save the day. Electricity, fuels burned in electricity specifically rather than energy generated by electricity. That distinction is important because depending on the accounting method that you're using, renewables will appear to be smaller or larger. Renewables operate, depending on how you account for efficiency, at like kind of triple non-renewable things. So you would see a significantly larger slice of this taken up by renewables if you were tracking something else here. So right around the same time period, 1945, 1950, is also when you get the huge expansion of the US electricity grid. In the United States, this is pretty much the period when all of the non-urban energy infrastructure is built. when you get the electrification of rural areas. It's also when you start to get the various kinds of like little balkanized individual corporate like grids. So like each corporation would be operating its own electricity grid. And this is the period when it starts to get integrated into a regional and then a almost national grid. And so there's a huge increase in demand for energy. And it just so turns out that as they're doing this, there's a fuel which is newly cheap in the form of coal. It moves around places via railroads, and because of the US's like longer history, there are railroads going to pretty much every city and town in the country. So electricity becomes the single biggest consumer of coal. Electricity burns in 2005 twice as much coal as as the entire economy did in 1915. So coal is actually massively increases over the course of the 20th century. It also shifts where the coal is mined and what kinds of coal are actually valuable. When you're burning it in your household, you want the cleanest burning coal that you possibly can, because obviously you do. And so you generally be burning kind of those harder anthracite coals mined in Pennsylvania, kind of the typical places that we think of as the coal mining towns that US politicians are constantly referring to and constantly catering to. But by the end of the 20th century and the early 21st century, most of that coal is instead kind of lower grades of coal, bituminous coal that you're mining out of the US West, generally through kind of larger and industrialized operations with a lot fewer workers. And so this is kind of the saving grace of coal. It's also kind of the saving grace of the electricity grid. Building it out would have been a lot more difficult and a lot different without coal, just because other fuels weren't necessarily as mobile. And you would have had to build a lot more like long range transmission infrastructure. So to me, this gives a few key insights. Number one, yeah, we've only been adding energy sources over time, but there are transitions that happen at the sectoral level, right? So if you like look at the residential sector, sure, we're burning as much firewood in the present day as we were in the mid 1800s, but the actual like lived experience of people and also the economy as a whole is obviously massively shifting away from firewood and towards coal, and then completely abandons coal as well. By the year I'm trying to remember, I think it's 1989, so like surprisingly late, but a while back now. The Energy Information Administration, who's collecting a lot of these statistics, records no coal burned in any household or any commercial establishment in the United States. So there's a complete extirpation of a fuel at that level. And at the same time, the electricity sector eventually also has a transition of its own, one which is still ongoing. So you'll notice that this graph is ending in the year 2021. If it kept going a couple of years, this kind of like pinching of the black, the reduction of coal being burned continues a little bit. And depending on policy of the current administration and how much it changes things, I think I would expect coal to kind of reach like 10% of the overall electricity production in the US. I believe I've looked at this and it's something like by the year 2030. It's a really rapid transition that's still ongoing. And a lot of this, not related to this project, but related to my other research, a lot of this isn't necessarily happening at the national level either. There's a lot of local campaigns against coal. A lot of this is being kind of mobilized by environmentalist groups who are kind of figuring out new legal strategies to kind of mobilize those permitting laws and kind of generic NIMBYism to call it. At the same time, a lot of what drove the reduction in coal use in the early 21st century is the fracking boom that happens post 2005 with new kind of technologies and new legal regime, which makes it a lot easier. So that is kind of how this transition happens. I also think point number two, that although this should give us some hope as to energy transitions actually existing, if they didn't exist, then it would be pretty dire. So the fact that they exist is pretty good. But it does give us kind of a strong note of caution in how we kind of think about energy transitions and also how we kind of plan energy transitions, right? There's this concept that we kind of came up with while we were looking at this of energy refugia, that after kind of being extirpated from the rest of the economy, coal finds a refuge in the electricity sector simply because it's so cheap and the infrastructure still exists. The stranded assets are there, and they pretty much just need a home, right? And if there is any particular place that an energy source can flow to as it becomes cheaper, we kind of expect it to get taken up by that via kind of simple laws of supply and demand. Yeah.
Yeah, you mentioned that like the type of coal being burned was changing. So can those stranded assets then like transition across different types of coal, or do you see some of those lost along the way?
So a lot of the bituminous coal that's getting set, or a lot of the kind of like extraction infrastructure for the bituminous coal is getting set up in kind of like the period right before this kind of shift to the electricity sector. But they're also burning a fair amount of Pennsylvania coal early on, and they just kind of run out of the cheap stuff in like, I think I would just be making it up if I gave a year range, but I think like mid to late 20th century. Yeah. Does that answer your question?
Yeah.
Yeah, great. Any other questions? There'll be a Q&A time at the end. The other way to kind of look at this, the way that I've kind of provocatively titled this presentation is zombie energy. Like you think you've killed coal, but the coal has come back to haunt you, right? This is a thing, this is a factor which I would not be surprised could happen with pretty much any of the fossil fuel regimes, just because the ways that these fuels are valuable is something that can be shifted from sector to sector of the economy. Effectively, what happened to coal over the course of the 20th century was we moved it out of the household, we moved it out of cities, and we moved them to electricity production facilities, which were just located in kind of like increasingly suburban and exurban areas. Via electricity transmission increasingly becomes hidden from the consumer. And it's the same story in the United Kingdom as well. It's the same story in most of continental Europe, mostly France aside because of its strong nuclear power sector. It's pretty much the same story the world over. Coal is generally not declined. Yeah. And then, so our current work wants to kind of introduce a level of granularity to this. So I find these stories interesting. I find them important for kind of like thinking about how energy transitions are shaped, how they're moving through the future. But there's not a lot of nuance to these, and there's a lot of geographic heterogeneity in the United States' energy system, right? There are areas of the country that are extremely coal rich, there are areas that are extremely gas and oil rich, and these transition between these fuels at different times. So what we're hoping to do with our current work is to kind of get at the geographic heterogeneity of it and kind of understand how is infrastructure changing, shaping, and driving these transitions. So our current work is focused on building a historical map of energy infrastructure. This is a current present day map. I believe if you go to the website, you'll find the interactive version. It's a little janky. It's in beta testing, so I wouldn't be surprised if it breaks on, every third axis or so, but certainly feel free to play around with it. It also has, like I alluded to earlier, asset values for each of these. So the total value of all of the electricity transmission lines, so the replacement value of them, the total asset value of all of the coal mines, all of the railroads. And one of the reasons for doing this is that we have a strong suspicion that this like zombie energy, this energy refugia, happens largely because the infrastructure already exists. The coal mines already exist, so too do the railroads. When you're talking about railroad corporations, too, pretty much the only things that they actually haul in the United States anymore are coal or wheat or ore. It's kind of those large bulk heavy commodities. So they have a strong incentive to kind of lower rates as well. And other energy supplies have their own highly specialized infrastructure. We'll get into pipelines a little bit in a minute. Of course, the electricity grid is this sprawling nest of various transmission lines of the different colors here indicate their voltage. So the black are like extremely high voltage, like over I think 500,000 volts, and then the kind of going all the way down to the extremely fine detailed, like yellow and white ones are the kind of more local transmission lines. And the dots here are all of the electricity generating stations color coded by their fuel. This one in and of itself is also another huge research project. And to talk about like how we're starting to put it together, I wanted to talk about pipelines. So this is a map of natural gas pipelines in the United States in 1931. Old maps will kind of chart how gas flows around various pipelines that are generally transcontinental in scale. All of these were kind of built out. The first layer, I would say, of US energy infrastructure was really built out in the early 20th century. And you can see with something like natural gas pipelines, it's extremely regional in scope. It's really only around those kinds of oil and gas fields that they're getting built. And then most of what is currently extant in the United States is actually built then over the next 30 years. So between the 1930s and the 1960s, you can see that there's a vast amount of infrastructure that's constructed for natural gas pipelines. So natural gas is, of course, hard to move by train or by boat. It's kind of a nightmare, as we're currently discovering with the pipeline problems in Eastern Europe. Liquid natural gas, also a bit of a nightmare. This is kind of outside the scope of my own research, so I only am aware of it. I can't really speak to it in great detail. But it does mean that basically the only way that people actually move around natural gas at scale or at like any kind of reasonable costing is through the construction of a pipeline network. This particularly happens in an explosion in the mid-century United States. And this allows people to kind of route natural gas to pretty much every small town of any consequence in the US and every kind of medium-sized city. What's also happening during this same period in history is the explosion of suburbia in the United States. Which leads to a really interesting presence of natural gas in the present day United States. So this is a map. This one was put together by the Washington Post using some of the residential energy consumption survey data from the US Census. And the natural gas is in dark blue here. The light blue is in propane. This is showing how the average person in each census tract heats their home. So you can see in the US South, which generally doesn't get that cold, it gets physically a little colder in most of the US South than it will get in Britain. But because it's dry cold and because that doesn't really last very long, nobody really puts that much energy into heating their home. Hence, electricity and electric resistance heating is pretty trivially easy. Same thing for the Pacific Northwest, which is also generally kind of easily heated. You'll see like large tracts of land in Alaska, which has oil reserves for days, essentially. And also in the northeastern United States, because of when they were installing the infrastructure, those rely heavily on oil. And then you kind of have the middle of the country, which has this patchwork of propane and natural gas. And if you remember where the kinds of extraction fields of natural gas are, you have this mid-continent region in the kind of Texas to Kansas area, and then the northeastern region around Pennsylvania and Ohio. Those are exactly the areas where rural areas are really leaning on this natural gas network. But you also see patches of natural gas everywhere. And this is because of when the transition happens and when that infrastructure is getting installed, right? So like the infrastructure is getting built out in the mid 20th century, which is exactly when those outer ring suburbs of the United States are getting built. So you'll see in almost every single metro area, this little ring of dark blue natural gas. So like you see it in Houston, you see it in Atlanta, you see it in Dallas, you'll see it in Phoenix, you'll see it in Seattle. In the northern US, you'll see like the entire metro area is natural gas heated. So there's this geographic heterogeneity that's really occurring, and it's occurring because of the timing of when the infrastructure is built versus the timing of when heating demand is coming online. And so this is one of the things that we're really hoping to get out of the out of expanding our infrastructure mapping into the past, to kind of figure out like when these things were installed, how much does that drive any individual transition, and how does that kind of drive those like larger scale energy transitions across the country that I was showing at the beginning of the presentation. Now, there are some problems with what we're currently doing. And the biggest problem is that these maps that were done are really not done that often. These are kind of large-scale corporate undertakings. This is by the Oil and Gas Society of the United States. They kind of just like survey companies, talking to them about when individual pipelines are built. There are, let's see, a handful in the 1930s. And then mysteriously during World War II, no one wants to publish information about where all your oil and gas pipelines are. And so the next one you get isn't until 1948. And that one is at a particularly low resolution. But even then, between 1948 and 1967, there's pretty much nothing. So it happens kind of on the order of decades. So this is a little bit too clumsy for us to kind of draw any real conclusions about energy infrastructure. So what we're hoping to do is to kind of figure out these transitions with more granularity. On the large scale infrastructure side, this is doable through kind of searching through like large digital newspaper databases. The Library of Congress has a really good one. Newspapers.com has another really good one. And you can actually see people generally reporting on there's a giant pipeline being built through our city. Whether it's positive or negative, or whether it's like talking about the workforce that's moving through, these are generally news items. And so we get a pretty good sense of when things are built. So using this, we were able to kind of push back the maps of these pipelines a lot earlier than anyone has been able to do before. Should have included one in this presentation, but didn't. So you'll get to see it later when this work is kind of released later on. The other thing that we're kind of hoping to do is to get at it through an entirely different source set of sources, one that I don't think anyone's ever used for this purpose, and one that I think is going to be a really interesting one. US fire insurance companies towards the start of the end of the 19th century and towards the start of the 20th century did extremely detailed building by building level maps of pretty much every town in the United States of consequence. They only did them every decade or so as well, but what they do is by doing all of these different towns at slightly different times, and also including generally the fuel used by a large building. So like we can look at this building from the 1880s and learn that it's burning coal. And by comparing whether or not that's unusual to neighboring towns, we can kind of get a sense of how fast are different towns transitioning from energy source to energy source. How much is this connected to the infrastructural links between them? How much is it connected to geographic proximity to those energy sources? And just kind of generally what is spurring these energy transitions? Like what causes somebody to choose a fuel like coal for their big hotel in the town or the city of Omaha, which is where this is from, versus gas, and when do they make the switch? And these are there are a sufficient number of these that I think we'll be able to get some really interesting data out of them. The other thing that's really fun out of this is using some kind of new machine vision technology. You can actually train computers to look for specific visual cues. And generally, the only things that are circular on these maps are tanks of something or other. Generally, they are either water or they're fuel. And so we'll be able to actually see the construction of this infrastructure in some really novel ways. There's like 6.5 million images in this digital database. So it's not something you can go through by hand to find this, but when you're able to kind of use technology to do it for you, it makes the primary source issue a lot more tractable. The other place that we're looking in is by combing through good old-fashioned text to kind of see when people are advertising different energy sources in different areas. So there are some really delightful advertisements that I have gotten to look through for like the natural gas industry, which is connecting gas with all sorts of like better living through gas. You know, you and your family who are all the platonic ideal of generally a suburban, white, middle class, heteronormative, like monogamous family. They're all going to be heavily on display here. But by kind of comparing how often these advertisements are happening in different places at different times, that's another layer of data that we can kind of add to get at that level of granularity that we're pursuing. So I think there's some time for questions here. I think there's plenty of time for questions, actually. But just to generally kind of sum up what I've been talking about today. So energy transitions generally do happen contra a lot of energy historians. This appears to be the hill that I will die on in my career, which I've already resigned myself to 1 year into a professorship. But they do happen at the sectoral level rather than the national level. You generally see like large groups of technologies adopt a specific kind of fuel, and you don't see them happening at the same time unless there's a specific set of things driving it. absent those kind of like bigger supply shocks, it seems like older fuels will generally remain in use. But it would be really, really good to get a lot more granularity on this, which is where a lot of the new digital methods that I'm kind of employing are coming in real handy. This is generally helping to kind of bridge quantitative and qualitative work, which has kind of been my hobby horse for a while, working with some scientists. So generally, I think that this work is potentially really useful on the policy front, but it also, I think, will illuminate a lot of energy history that has previously gone a little bit under-examined. So thank you. Yes.
Just maybe explain one more time how or what you expect to learn from looking at historical energy transitions. So, for example, the example you gave now, transition away from coal and what contextual circumstances, what impact they have. Why is this relevant compared to looking into, okay, what happens right now and how to populations transition from fossil fuels to renewables, right? You could also look at that data and it's closer, and I guess there's also more data available for that.
Yeah.
Just explain to me why you think the other one is very important.
Absolutely. I think the reason to look at historical data is partly just to get more data and also to see things that were actually successful versus things that were not successful. That reminds me, this is going to cause me to scroll all the way back. But to talk about, oh, I hate that it's at the top of the graph. I'll try and put fission down at the bottom of graph for a specific reason. There are also examples in here of failed energy transitions. So you see them starting and then they stop. So generally in the energy transitions literature and kind of like sustainability journals and in policy journals, everyone kind of recognizes that things happen as logistic curves where they start out like not particularly adapted. They slowly ramp up. You go through a rapid period of transition. And then ideally it displaces whatever it can in the area and maxes out close to 100%. The logistic curve for nuclear fission tops out like at about like 10% of the US energy supply, and then it just stops there. And obviously there are a lot of exogenous factors related to this, like Chernobyl, 3 Mile Island. But a lot of this is just because of the ways that the policies were implemented at the national level. There's specific ways that the US government is investing in engineers and is investing in education that actually causes nuclear to be a lot more expensive even before all of those environmental costs. So comparing that kind of thing with a more successful energy transition, similarly, comparing kind of like the infrastructure build out of natural gas and the way that it relates to its transition. So you'll note, again, these are kind of hard to see because of the volatility of the coal supply. So it's like not always clear when something is kind of a consistent line. Natural gas has a huge explosion in use in the early 1910s, where it like suddenly starts to be like a solid 10% of the energy supply as well. And then it stops there for like 50 years and it never really goes anywhere. And a large part of that is because the infrastructure isn't built out, right? Which is a thing that we are starting to see happen with the renewable sector in the present day. There are transmission bottlenecks and kind of those large high voltage lines. But we haven't really seen the endpoint of that, whereas you do see the endpoint of this. I would say my field has trained me to never say that history is a precise analog for the present, and obviously it's not. There are always going to be like very specific factors that are fueling, pun intended, different energy transitions. But I think there are kind of larger generalizable lessons about how a government can kind of manage supply and kind of manage throttling up and throttling down on different energy sources. And it's kind of those more generalizable lessons that we're pursuing. So, yeah.
Yeah, just maybe to try to like put it in my own words so I can help understand it.
Mhm.
Kind of answering this question and synthesizing what you just said there. So it's kind of like you're learning from the failed energy transitions to understand, why, so that we can maybe inform for these future energy transitions, what not to do. But then also maybe getting more information about the successful transformations on, how much they cost, what were the circumstances under which that was allowed to occur. Because at least from the pipeline map that, and you mentioning the difficulty of that seems like if you had an accurate map, you'd be able to do a pretty reasonable estimate of how much that cost, right? And
Yeah.
the, like something you can quantify over time to then be to not underestimating budget, as is almost always the case with like every single project ever.
Exactly. Yeah.
Yeah.
Yeah, like how do you get a company to abandon like $500 billion in stranded assets? Well, not a company, but like an industry to abandon $500 million or $500 billion. Sorry, that number is important to get right. $500 billion in stranded assets. Like, are there like examples from history where you can do that? How do you get them to kind of, how do you get like individual consumers to become familiar with the technology? So one of the things from energy history that we see a lot of in kind of the more qualitative literature is how much work it is to get somebody to actually like start using a new thing in your home. Like we see this in the present day with heat pumps. Like a lot of people are convinced that like heat pumps in the house are going to be like heat your home slower. They're going to be like more whatever. They're not going to work in like cold weather. You see the exact same kinds of anxieties around like the adoption of coal, actually, like after firewood, like people switching to coal. Surprisingly, people were just like, I have no idea how to like use this fuel. Coal is actually like kind of a finicky fuel, which is something that I discovered over the course of this research. Like I always kind of assumed you could just build like a fire out of it the way you build like a wood fire. Nope, turns out like it won't ignite except at like really high temperatures. So you need specialized equipment for it. You need specifically to kind of like learn how to get a coal fire started. So all of these kinds of like consumer end technologies, but also like industry ones, like they have to kind of learn how to live with them, right? Did you have a question?
Yeah. Do you see like discrepancies in energy transitions across demographics in the US, say like
Mm.
an inner city demographic adopting an energy layer, or maybe like reservations, for example? Have you gone into that direction at all?
Yeah, I'm hoping to do a lot more of that. I haven't yet. I would suspect there are pretty big ones. I mean, like the income available on like, like the per capita income on the Lakota reservations in South Dakota is something like an order of magnitude less than the per capita income of the average person in the US. So of course they're not going to be able to install the latest energy technologies, and you're constantly hearing of them being unable to keep up with utility bills. I think that would be one thing for which granularity of data would be wonderful. Hence what we're doing now. So, but yeah, no, I think that's a really astute observation. Yeah. Yeah.
Maybe a request for another reflection. So you
Mhm.
seem to have read a lot of corporate documents of when the coal industry started to realize we're running out of our basic business model. I would be interesting to hear from you on whether you feel like there's a similar situation now, where the
Mm.
fossil fuel industry is scrambling to avoid stranded assets, and whether there are some similarities that you see between how they reacted back then compared to how they react now. Just to give an example, recently India offered to start offshore oil drilling and gas drilling, simply because now it's still possible to sell fossil fuels. Well, probably if they wait 25 years or something like that, no, it won't be possible.
Mm.
So how does this fear of stranded assets affect corporate players?
Oh, I mean, like, I'm not in Exxon's boardrooms, right? I suspect I won't ever be. So it's hard to know like internally what's going on compared to like a century ago. Yeah. I mean, I think there are a lot of similarities in the ways that they're reacting. I think you'll see a lot of similarities in like kind of addressing directly a lot of the concerns that people have with like household use. You'll see a lot of greenwashing with like specific kinds of larger electricity suppliers. So like in the 1950s, like every new coal plant that was built emphasized kind of like the new technologies that were going to cause it to like not be particularly harmful to the local environment. They'd emphasize the environmental studies that they'd done to indicate that it wouldn't be harmful to the local wildlife or to the local population. Um, and also that it would be like in kind of a remote area, so it wouldn't matter that much. You'd also see around the same time any kind of like larger pollution concerns played down in kind of the same ways that we talk about carbon in the present day. Um, I would say a lot of this is happening. I mean, as the documents that we keep discovering keep pushing back the timeline on like when people learned earlier and earlier, and so they were doing that exact thing rather than an analogous thing like by the mid 20th century. Yeah, those would be some of the examples that could immediately come to mind. I think like in terms of like the really, really like down in the weeds stuff, a lot of the like coal advertisements that I see in the like mid 20th century read I wish I had the exact words coming to mind, but they kind of have the same vibe as like natural gas, like paying influencers to use like gas stoves in their kitchens, like very like, oh, make sure you like check this out, kind of like don't think of this fuel as like an old-fashioned fuel or that sort of thing. Um, yeah, I think that's a good answer to that. If you want a fun book recommendation, one of my colleagues from a prior university, Trish Kashla, has written a book called Energy Citizenship, and it's all about coal and like the kind of ways that the industry navigates the kind of turbulent times of the mid 20th century. So that would be a great read. Yeah, is there an online?
Use the use of coal?
Yeah, I would love to comment more on that. I haven't like done a thorough enough job looking at the environmental policy. What I can say is that the EPA rules that come online kind of in the middle of the coal building boom, so kind of that like 19 well, not the EPA at the 1950 point, but between 1950 and 1980, as more environmental regulations come into effect, you do see a lot more kind of peripheralization of coal generation. So it's kind of moving outside of cities and towards kind of like more rural spaces, explicitly to what's the word? To comply with government regulations. So yeah. Any other online questions? Anyone else in here? Yes, I think this might be the last question because we have to clear out right at one. So
You mentioned several times that stranded assets.
Mhm.
And assets. I would like to hear from about how it happens, how industry starts to realize like how things unfold. Seems like people can't expect that the transition is place, and then all of a sudden, transition like curve, and then at some point, very very fast.
Mhm.
And I would assume investors see that happening, so they're going to divest these shares as soon as they feel that it's happening, like a bank run, right?
Mm.
Trying to run away from these companies, and then the industry collapses instead of being a smooth transition where it seems like this is a smooth transition. coal did not get into this stranded asset overnight situation.
Yeah.
Just like, we'd like to hear you.
Yeah, I mean, I think the reason that it's not as sudden of a transition, this is a great question that I'd love to get into for like 10 minutes, but I have two, so this is going to gloss a bit. I think the reason that you don't see it, and this is still something I'm working on and thinking about for my own writing, but I think the reason that it's smoother than you'd expect is in part because this is a national scale thing and the infrastructure exists to move energy around. And so individual places will kind of transition away as it becomes cheaper, as the new infrastructure is built out. So like in theory, assuming a a full steam ahead kind of transition to like renewables, you would see that happen gradually and heterogeneously, geographically speaking, because certain places are considerably better for renewable development. So like the wind infrastructure, like would be really good in the Great Plains. That's where most of the wind is, but you can see there's no kind of like high voltage power lines built between them and the rest of the United States. So you would kind of see these areas move away from natural gas faster. You'd see areas that could rely on solar move away from it and towards renewables first. And then only after that would you start to see kind of like the other areas of the country follow, probably. Hard to future cast, but that would be my expectation. It's a very similar story, I think. Haven't done all of the geographic differentiation for coal in the mid 20th century, where it goes away from specific areas where you can install those kinds of gas infrastructure first, and then only later does it kind of spread. I think that's time. So thank you all.